Welcome to Section 3, Lesson 5. Across the previous 4 lessons, we solved linear equations using inverse operations applied identically to both sides. Today, we extend the same toolkit to linear inequalities, where the equals sign in our equations is replaced by a less than, greater than, less than, or equal to, or greater than or equal to symbol. The solving procedure is essentially the same as for equations, with one critical exception that you must memorize and never forget: multiplying or dividing both sides by a negative number flips the direction of the inequality. Today's lesson covers that flipping rule in detail, walks through 2 clean examples, and shows how inequality solutions are expressed as ranges of values on a number line rather than as single specific numbers. First idea on the board. A linear inequality has the same structural form as a linear equation, but with one of the 4 inequality symbols in place of the equals sign. 2x plus 5 less than 13 is a linear inequality. 3x minus 7 greater than or equal to 2 is another. The solving goal is the same as for equations: isolate the variable on one side. The difference is that the result describes a range of values that satisfy the original inequality rather than a single value, and the solution is typically written as a range, an interval, or a graph on a number line. The solving procedure follows almost exactly the same inverse operation workflow as for equations. Apply the inverse of any addition or subtraction first to both sides. Apply the inverse of any multiplication or division next to both sides. The reverse PMDS order from Lesson 2 carries over directly. The both sides discipline carries over directly. The only structural change is the new flip sign rule that triggers in one specific situation, which is the topic of the next idea. Third idea, the flip sign rule says whenever you multiply or divide both sides of an inequality by a negative number, you must flip the direction of the inequality symbol. Less than becomes greater than becomes less than or equal to becomes greater than or equal to. The flipping is required because multiplying both sides by a negative number reverses the relative order of the 2 sides on the number line. The rule is small and easy to remember once you see why it exists, but forgetting it is the single most common error in beginning inequality work and produces wrong answers that look right at first glance. Today we lock in the rule with one no-flip example and one flip required example side by side. A linear inequality has the same structural form as a linear equation, but with one of the 4 inequality symbols in place of the equals sign. The 4 symbols are less than, greater than, less than or equal to, and greater than or equal to. Solving means isolating the variable on one side, and the result is a range of values that satisfy the original inequality rather than a single value. Here is the solving procedure. Apply the inverse of any addition or subtraction first to both sides, exactly as you would for an equation. Apply the inverse of any multiplication or division next to both sides. The reverse PMDS order from Lesson 2 carries over without modification. The both sides discipline carries over without modification. Almost everything you know about equation solving transfers directly into inequality solving. The one critical exception is the flip sign rule. Whenever you multiply or divide both sides of an inequality by a negative number, you must flip the direction of the inequality symbol. Less than becomes greater than, and vice versa. Less than or equal to becomes greater than or equal to, and vice versa. Adding or subtracting from both sides never triggers the flip, only multiplication and division by a negative number does. Memorize the rule and apply it consistently every time the trigger condition is met. Step 1 in the workflow. Identify the operations applied to the variable. In the inequality 2x plus 5 less than 13, the variable is being multiplied by 2 and then 5 is being added on top. 2 operations stack exactly as in a 2-step equation, and the inverse procedure will undo them in reverse PMDS order with no flip needed because we will be subtracting and dividing by positive numbers. Step 2 and beyond. Subtract 5 from both sides to undo the addition, giving 2x less than 8. Divide both sides by 2 to undo the multiplication, giving x less than 4. The solution is the entire range of values strictly less than 4, written as x less than 4 or as the interval from -infinity up to, but not including 4. Verify by picking a test value in the proposed solution range, like x equals 0, and confirming the original inequality holds 2 times 0 plus 5 equals 5, which is indeed less than 13, so the solution range is verified. Here is the first worked example. Solve the linear inequality 2x plus 5 less than 13. The variable is hidden behind a multiplication by 2 and an addition of 5. The procedure is the same two-step inverse from lesson 2, with no flip required because the multiplier 2 is positive. Step 1. Identify the two operations applied to x. The variable x is being multiplied by 2, and then 5 is being added on top. The inverses are subtraction and division, in reverse PEMDAS order, subtraction first, because the addition was the outer layer. Step 2. Subtract 5 from both sides of the inequality. The left side becomes 2x plus 5 minus 5, which simplifies to 2x. The right side becomes 13 minus 5, which equals 8. The inequality is now 2x less than 8. The inequality direction did not change because subtracting from both sides never triggers the flip rule. Step 3. Divide both sides by 2 to undo the multiplication. The left side becomes 2x divided by 2, which simplifies to x. The right side becomes 8 divided by 2, which equals 4. The inequality is now x less than 4. The inequality direction did not change because the divisor 2 is positive, so the flip rule did not trigger. Step 4. Verify with a test value. Pick any value in the proposed solution range x less than 4, like x equals 0. Plug into the original inequality. 2 times 0 plus 5 equals 5, which is indeed less than 13. The original inequality holds at the test value, so the solution range is verified. So the solution is x less than 4. The big lesson from this example is that the standard two-step inverse workflow handles linear inequalities exactly the same as linear equations when no negative multiplier or divisor appears anywhere in the procedure. The verification step uses a test value rather than a single substitution, which is the natural extension of the substitution check from equations to inequalities. The solution can also be written as the interval from -infinity up to, but not including 4, or graphed on a number line as an open dot at 4 with shading extending to the left toward -infinity. All three representations describe the same range of values. Here is the second worked example. Solve the linear inequality -3x plus 4 less than or equal to 13. The variable is hidden behind a multiplication by -3 and an addition of 4. The new feature this example brings is the negative coefficient on x, which will trigger the flip sign rule when we divide by it at the end of the solve. Step 1. Identify the two operations applied to x. The variable x is being multiplied by -3 and then 4 is being added. The inverses are subtraction and division. In reverse PEMDAS order, subtract 4 first, then divide by -3. Step 2. Subtract 4 from both sides of the inequality. The left side becomes -3x plus 4 minus 4, which simplifies to -3x. The right side becomes 13 minus 4, which equals 9. The inequality is now -3x less than or equal to 9. The direction did not change because subtraction never triggers the flip. Step 3. Divide both sides by -3 to undo the multiplication. This is the step where the flip sign rule triggers because the divisor is negative. The left side becomes -3x divided by -3, which simplifies to x. The right side becomes 9 divided by -3, which equals -3. The inequality direction flips from less than or equal to into greater than or equal to. The result is x greater than or equal to -3. Step 4. Verify with a test value. Pick any value in the proposed solution range x greater than or equal to -3, like x equals 0. Plug into the original inequality -3 times 0 plus 4 equals 4, which is indeed less than or equal to 13. The original inequality holds, so the solution range is verified. As a bonus check, also try a value outside the range like x equals -10, -3 times -10 plus 4 equals 34, which is not less than or equal to 13, confirming that values below -3 are not solutions. So the solution is x greater than or equal to -3. The big lesson from this example is the flip sign rule in action. The rule is triggered exactly once during the solve, at the moment of dividing by a negative number, and the inequality direction must flip at that exact moment. Forgetting the flip is the single most common error in beginning inequality work and produces a wrong solution range that looks right at first glance. Build the habit of pausing whenever you multiply or divide both sides by a number with a negative sign and explicitly flipping the inequality direction at that step. The pause and flip habit becomes automatic with practice and prevents the most expensive inequality error in the entire algebra course. 3 mistakes that catch every algebra student during their first weeks of inequality work. Each one is fixable with a small explicit habit applied on every solve. First mistake, forgetting to flip the inequality direction when dividing or multiplying both sides by a negative number. A student solves -3x less than or equal to 9 and divides both sides by -3, getting x less than or equal to -3 instead of x greater than or equal to -3. The arithmetic is correct, but the inequality direction is wrong, and the proposed solution range is exactly the opposite of the true solution. The fix is to pause every single time you multiply or divide by a negative number and explicitly flip the inequality direction at that step. Build the pause and flip into your standard solving rhythm. Second mistake, flipping the inequality direction when the trigger condition is not met. A student solves x plus 5 less than 10 by subtracting 5 from both sides and flipping the inequality, getting x greater than 5 instead of x less than 5. Subtraction never triggers the flip rule, only multiplication or division by a negative number does. The fix is to read the rule precisely. The flip happens only when the multiplier or divisor itself has a negative sign, not when the inequality has subtraction or negative constants on either side. Third mistake, confusing the strict inequality less than with the non-strict inequality less than or equal to. A student solves an inequality with a less than or equal to symbol and writes the solution with a strict less than symbol, dropping the boundary value from the solution range. The fix is to copy the inequality symbol carefully through every step of the solve and confirm at the end that the symbol matches the original. The boundary value matters. X less than or equal to 4 includes 4, x less than 4 does not. Linear inequalities are even more common than linear equations in real-world applied work because real systems usually have constraints expressed as upper or lower limits rather than strict equalities. 4 broad sectors below. In engineering tolerance analysis, every component must satisfy stress, temperature, and pressure constraints expressed as inequalities. Stress less than or equal to maximum allowable stress, temperature less than or equal to maximum operating temperature, pressure less than or equal to burst pressure. Solving these inequalities for the maximum acceptable input load or operating condition is a standard linear inequality solve, and engineers do this kind of work on every design review. In personal finance and small business budgeting, total spending in a category must stay less than or equal to the budget allocated to that category. Total spending equals number of units times unit cost, so the inequality is a linear inequality in the unit count, and solving for the maximum unit count given a fixed unit cost and a budget cap is a clean two-step solve. Anyone managing a budget in any context does this calculation regularly, often without recognizing it as the linear inequality algebra they learned in this lesson. In transportation and safety engineering, vehicle speed must stay less than the posted speed limit, and acceleration must stay less than the maximum safe acceleration for the road conditions. The relationships often involve other variables like distance and reaction time, all linked by inequalities that need solving for the maximum safe input value. Aviation, marine, and rail safety engineering all rely heavily on this kind of inequality work. In linear programming and operations research, optimization problems typically involve dozens of linear inequalities representing capacity constraints, demand constraints, budget constraints, and resource constraints, all to be satisfied simultaneously while maximizing or minimizing some objective. The simplex method and other linear programming algorithms manipulate large systems of linear inequalities using essentially the same balance and inverse logic you are learning today, scaled up to many variables and many constraints. The skills you are building this week underpin a vast professional discipline. 3 things to take with you from this lesson today. Linear inequalities are even more common than linear equations in real-world applied work, and the small extension of the equation solving procedure that we covered today scales the entire Section 3 toolkit into the inequality world without any other modification. First, inequality solving uses exactly the same inverse operation procedure as equation solving across the previous 4 lessons. Identify the operations applied to the variable, apply the inverses in reverse, PMD's order to both sides, simplify each side after each inverse step. The both sides discipline carries over without modification. The gather step for variables on both sides carries over without modification. The literal equation procedure for solving in terms of letters carries over without modification. Second, the one critical exception is the flip sign rule. Whenever you multiply or divide both sides of an inequality by a negative number, you must flip the direction of the inequality symbol. Less than becomes greater than, less than or equal to becomes greater than or equal to, and vice versa. Adding or subtracting never triggers the flip. Only multiplication and division by a negative number does. Build the pause and flip into your standard solving rhythm so the rule never gets forgotten. Third, the solution to a linear inequality is a range of values rather than a single value, and the solution can be expressed as an inequality, as an interval, or as a graph on a number line. Verify your solution with a test value drawn from the proposed solution range and confirm the original inequality holds at that value, then optionally also test a value outside the range to confirm the inequality fails there as well. The 2-test verification is the inequality world equivalent of the substitution check from equations and is just as fast and just as effective at catching solving errors. Coming up next, the lesson called Compound Inequalities, where 2 or 3 inequalities are joined together with the words and or to describe a more complex range of values, and the solving procedure stacks the Section 3 inverse techniques on top of a small new piece of structure handling the connectives. Compound inequalities are the natural completion of the inequality work we previewed today, and are the form you will see most often in word problems and applied constraint analysis from this point forward.